Well, let me move these things away. Okay, today we are going to talk about gears. And I'm sure all of you know what is gear, have seen gears, and have seen them in many applications. So gears can be in your kitchen. Let's say if you have a grinding machine, grinding things like a meat grinder, or in your car, gearbox, in your clock, and everywhere. But why do we use gears in the first place? To transfer power. Let's say if I have a motor, so of course it can be a small or gigantic motor, it may not have enough power that I need. Usually motors run very fast, but the torque is small. And I may need to change the torque to a larger torque. So initial solution is to use a belt and pulley, like two pulleys like that, and a belt around them. Like this. And here is the top view. Now from a small radius getting to the larger radius, so the larger radius getting a small angular velocity, but larger torque. So I'm transferring power from one shaft, which is the motor, to another shaft here. So belts are good, belts and pulleys are good. However, they require maintenance, the tension for the cable, for the belt, and they get loose. Also, they worn out very fast. Besides, they requires a lot of space. So you can imagine from a motor from this point, getting there, I need a length like this big. So another solution is to use gears. So instead of transferring power from a small to a large pulleys, now we'll switch them by gears. And I have lots of gears here. So a gear transfer power from one shaft. When we talk about the shaft, like one shaft here, which now you see it perpendicular to your screen, to another shaft. So from one shaft to another shaft. And we can have several of them, depends on our application. So the first gear rotates the second one, and so on. And of course, when we talk about a shaft and a gear, so the gear is going to be tight fit to the shaft. Let's say something like that, tight fit. Let's say in this scenario, I can glue them, but in industry, they are going to be press fit. And sometimes people use brackets or welding to fix the gear to the shaft. But then the shaft is not going to just rotate on a, let's say, loose surface. You're going to use bearings, and these are like mini bearings. So the one that you see in your textbook or in the problem that we solve, we show it as this shape. Like so, these 2 points to fix it on the table. Let's say I have a shaft. The shaft goes into the bearing, usually tight fit. And then there is a screw, so I can fix these two together. And now it rotates easily because of the ball bearing that is there. So, and let's say I have my gear. The gear goes tight fit there, right? Tight fit there. And then the second bearing is go there, right? And they will be fixed on the table. So this shaft now can rotate easily, all right? And the gear is there. So, but for now, we simply say that we have two gears, one on each shaft, like the one that I'm showing you. And if I rotate one, the other one is going to rotate. So I can have a small gear and big gear. Small gear, usually we call it a pinion, and the larger one, we call it a gear. So if I go from a small to large, the speed decrease, but the torque increase. Or it can be the opposite. My motor can be attached here. So if I rotate it, so the black one now rotates faster, but it's gonna give me a smaller amount of torque. Remember, always the power is gonna stay the same. And the power, if you recall, was T torque multiplied by omega, right? T multiplied by omega. So if one of them increase, the other one decrease, because we assume always the power stay the same. Conservation of energy. So two gears, they can be simple gears, or let's call them, the terminology that people use, spur gear. Spur gear is the one like this one. If you guys can see, the teeth are parallel to the main axis. The teeth and the shaft, they are parallel. The edge of the teeth, maybe not clear here. The edge of the teeth and the shaft, they are parallel. In comparison, we can have helical gear. For a helical gear, as you can see, the edge are not parallel to the shaft. There is an angle between edge of each teeth and the main shaft. And we call them helical gear. So as you can see, one is left angle, another one is a right angle. So helical gear, they are very similar to spur gear, no difference, except helical gear are smoother because of the this angle that they have. They involve in each other gradually, and the motion is smoother, less noise, but of course they are more expensive to make because of the shape of the teeth. So gears can be made out of plastic, of course, for toys or small applications like this one. And the process to make them is injection molding. You guys in manufacturing, probably either in your future course or maybe in your past course, you learn about injection molding. If you are in mechanic, I will see you next year in 392, which is the manufacturing processes, and we'll talk about injection molding. But basically, you melt plastic and you inject it to the shape that you want, which is a mold, and you make them. When it comes to metals, casting or other process like powder metallurgy or CNC machining is the way to make gears. Recently, because of 3D printing, you can 3D print a gear. Like, for example, this is a gear made out of stainless steel, and I 3D print it. It's a helical gear. And this is like the base. I just want to test if the 3D printer, metal 3D printer can handle that. So gears can be all in one plane, like the scenario that I have here, from one shaft to another, and all of the gears are in one plane. Or the gears can be in parallel plane. It means, let's say, I'm transferring power from one shaft to the second one, like this one. And now maybe for some reason, I need to transfer power to another shaft, which is, let's say, is not in the same plane. Let's say if I can, need to be tight fit. So now I have two gears here, parallel to each other. The first one is rotating the second one. And let's say I have another gear there. All right. So I have the gears in two different planes. And the power comes from the first one, let's say here, rotate this one. these two are going to have the same rotation speed, right? And then everything gets here to my hand. All right. So, and speaking of materials, of course, now with advanced materials like a carbon fiber, like this one that I have is a carbon fiber, 3D printed again, and it's super strong. Like it's even stronger than steel. There is no way that I can bend it. I forgot the number, but something's megapascal, I guess, or gigapascal. Oh, gigapascal, in the range of gigapascal, the bending strength that I need to bend it. And when we have this material, the carbon fiber and 3D printing, of course, we can make super strong gears in any complex shape or any size that we want. So with motors, sometimes there is a gearbox built in inside, like this one. I guess I showed you guys it before. It's a tiny motor, and then on the head there is a gearbox. Sometimes people call it gear head. So next time you are buying a let's say a servo motor or a stepper motor, check if it has a gearbox or gear head. So if it has a gear head, then it does something. For example, this motor for me, without this gearbox, is going to rotate super fast. But adding this gear head to it, now it rotates very, very slow, but it's going to be very, very powerful. And if you guys can see probably here, let me zoom a little bit. There are lots of tiny gears, and they are parallel to each other, and they have been combined. So without damaging the gears, we'll get to a large torque. So you may ask, okay, can I use a tiny, tiny gear, let's say this one, with a very, very large gear like that one? Of course, that's possible as long as there is a relation between the number of teeth, which we'll talk about it, and the radius between them. And technically, we say these two gears are meshed together. I can use a very small gear and mesh it with a very large gear. That's possible. So then I can transfer a torque from here to this one and make a very large torque. However, if I do so, the tiny gears is gonna be weak, and maybe after a few hours of working, this gun is gonna get fatigue. And yes, materials, they're gonna get fatigue. It's called fatigue stress, and it's gonna be, it will break. So, or it may not handle the stress that we need because it's small. So instead, what we will do, first, we transfer power from a tiny gear to a maybe average size gear, and then we will get to a bigger one. Something like that. And sometimes if you want to do that, let's say several times. So maybe if I want to do it appropriately, I will get from a small, a little bigger, and then another bigger gears, and then I'll get to a larger gear. Okay, so this is the appropriate way to do it. So you will see in a formula that this system will do the same things as this system is doing, transfer the same power. However, we have these middle gears there, and their task, they are just redundant in terms of kinematics, but their job is to reduce the forces that get into this tiny gear. But if I use this setup, it will take a lot of space. So that's why people use parallel, like two parallel gears. Like we will go from there to there, and then from this shaft to another one, which is going to be parallel to that. And you will learn how these things will be designed. That's the purpose of like this course and this topic. And that's why the gears here, they are parallel, so they are compact. Okay, so with that introduction, let me check. Somebody had a question in the chat. So the real world efficiency of the gears or the power. So that's a good question. The answer depends how much money we spend for manufacturing the gears. So it can be a range of, let's say, if you're buying a Swiss watch, right? Those excellent gears, accurate gears, so they are super efficient. If they are like lousy gears, the tolerance is not good, then the efficiency, of course, is not good. Of course, between gears, there is friction and that lost efficiency. But as a rough number, you can think of 80% efficiency, which again, we'll talk about it a little bit in formula. What do we mean by like 80% or 85%? Okay, so with that, let's me switch back my camera. Okay, here I am again. And let me share my screen. Minimize myself. And then where is my screen? Okay, this is what you guys want to see. Gears is one of my favorite topics. And it is important. Again, you need to learn it by heart. So lecture 28 to 31, 4 lectures, approximately, depends. We'll see how fast we go. It's going to be on gears. All the slides is on Canvas if you just want to follow along and fill it, the sections with me. But I will post the notes later when we're done with the last lectures. And the recorded lectures, of course, are going to be available. So what we are looking after in this course for these topics, because gears by itself, it can be a course. Okay, so your expectation in this course, first, you're going to become familiar with basic terminologies in gears. So next time you're buying a gear, so you know what they are talking, if they are talking about, okay, you need a gear, what's the pitch number? So you need to know what do they mean by that? Or they may say, okay, what is the diameter of gears? Like a lousy, let's say a person who doesn't know too much about gears, he thinks maybe when we talk about the diameter of a gears, it's that outside diameters, but it's not that outside diameters. So some fundamental terminologies. And then you'll become familiar with 4 types of gears, like spur gears, helical gear, worm gears, and then bevel or conical gears, and their applications. Very briefly, the focus of our lecture in this course is going to be part 3, which is when you want to design a gearbox, getting from one speed to another speed, what should be the input and what should be the output. For example, if I want to go, let's say, this is my input. Let's say this is where the motor is attached. And this is the output shaft. Omega output. We want to know the ratio between these two, and or if we want to design a system, a gearbox, how we should arrange them. There are 4 possible configurations: simple, compound, and planetary gear. So that's going to be the focus of our course. So just to let you know, we're not going to talk about specifically about gear design. Gear design is your future course, MEC 325, I believe, or 326, one of those, which You calculate the stresses in gears, you design gears based on the material and the shape of the teeth and those sort of things. Please study chapter 11. If you have time to study the whole things, that would be great, but it's essential to go through section 1 to 5, all of that. Skip chapter 12, unless again you have time. Skip 12, or maybe in summer you can study it. It's gonna help you a lot for designing gear, and in your future courses, you will be a hero if you study chapter 12 before getting those courses. You're gonna be ahead of other students. And then chapter 13, study all of it, entire chapter, all the examples and all the problems at the end. It's super easy and it's fun, but it takes time. Please go through that. So as I said, we will use gears to transmit power from one shaft to another. Like in this scenario, maybe the motor is over here and then the output is there. So this is our omega input and this is the omega output. As you can see, we combine these gears and it's, if you look at the picture, it looks like they are helical gears because the teeth are not parallel, right? Again, the way that they have been combined, you will see the input and output, they are not parallel to each other. They are like they have this 90-degree angle, right? We can arrange the gearbox in different ways so they have different angles. And so the input power, of course, is torque that we put in multiplied by omega in. Right? It has been connected to a motor. The motor has a speed and it has a torque. And then we are at output. We will get a torque out here. And then we're going to have a power then, or output power, let's call it. Output power. Again, it's going to be T out multiplied by omega out. Depends on our design. Maybe we like to increase the speed, or maybe we like to increase the torque, which usually that's the case. We like to increase the torque. So our assumption is the energy is going to stay the same, like the power in is equal to power out. So it means T multiplied by omega in is equal to T multiplied by omega out. So that's in theory. And as Felix mentioned, they are not always 100% efficient. So usually we multiply it by E, and this E stands for efficiency. All right. And if the question gives you the efficiency, for example, 80%, so you multiply it by 0.8. If the question didn't say anything, it means E is equal to 100% efficiency. And again, if you just look at the main part, let's say in theory, if you increase one, let's say from input T omega, maybe you have a higher speed, then depend on your design, you may get a slower speed, but larger torque. So spare gears, as I said, the simplest one, the main feature of spare gears is the gears, the teeth, they are parallel to the main axis, right? Let's say if you look at the edge of each, and then the main axis, they are parallel to each other. And they are called a spare gear. So when you look at two gears, all right, two gears, the picture at the bottom, you can visualize that there are two cylinders. They are rolling on top of each other. Keep in mind, these two cylinders is not the outside edge. So if you can visualize these two gears, on the picture on the top, you will see two little dot circles. Maybe it's not very clear. So it's not the outside and it's not the inside diameters. Maybe let me show you these things. Okay, yeah, better. I guess you guys can see my screen. So as you can see, there are two gears here. Okay, this is the side view, and this is like the front view here. You will see these two circles, one here, another there, right? So when I'm rotating these two gears, you can visualize that these two circles are rolling like with each other, right? They're rolling. Okay. So again, visualize always when two gears are working that there are two circles working together. And this circle is not again the outside diameter circle, or it's not the inside diameter. It's like an imaginary circle, something between them. Yeah. Or let me do this, then you can see it better maybe. Yep. So two cylinders, right? When I'm rotating these two gears, as you can see these, you can visualize that these two cylinders, they are rolling against each other. All right. Get rid of them. Now we have our gears. So this is a spare gear. Again, the edges parallel to the axis. But let's say for a helical gear, like this is a helical gear. If I look from the top, the edges, they are not parallel to axis. So there is an angle, and that angle is called helix angle. Now, if I rotate these two gears, can I rotate them? Yeah. You'll see they are gradually involved to each other like that. Or 3D view. Like something like that. And since they are gradually involving with each other, then they are going to be like, let's say, smoother and less noisier. So next time you are buying gears, buy helical gear, pay more money, and it's worth it. Another advantage of helical gear is you can use the same widths of gear, like the same widths here, as you can see from left to right, but the base is, it has a bigger area. Let's compare it with this guy. Like if I measure the thickness of this gear, let's say from here to over there, it is 10 millimeter. And the second one also is 10 millimeter. If let's say I measure from this side to this side, oh, it measures something perpendicular. Anyway, so maybe I cannot get it done in one shot. The same thickness, the same widths, but now for a helical gear, we have a bigger area. So the teeth are stronger. A lot of advantage, but of course they are more expensive. So let's get back to the idea that when we think about the two gears working together, think about two cylinders rolling against each other, and there will be pure rotation between them. Okay, so that's what it's about. As I said, the small gears, we call it a pinion, and the larger one, we will call it gear. So that's just the basic naming. Always the small one, we call it pinion, the larger one, gear. Those two cylinder that I talked to you, they call them pitch cylinder. Previous slide, we will call them somewhere there, pitch cylinder. And here they will be called pitch circle, two imaginary circle, right? They are not actually exist. So the radius of one of these gears can be infinity. And if that's the case, we will call it a rack. So the gear on the left is just a gear and pinion. The one on the right is pinion and the rack, right? Remember, always the small one, we'll call it pinion. And then the large one, here in this case, instead of gear, some people call it a comb, or just simply gear. Sorry, rack. Or it is a gear with a radius of infinity, or a very, very large radius. So every formula, everything will be the same, except now the radius for this one is infinity. How gears are made? Again, in your future courses, you will see more, but casting is the most common, sand casting. If you want a more accurate, go with lost, it is lost wax. So I need to correct this, guys. So it is not was or was, it is wax. So lost wax or investment casting, die casting, powder metallurgy recently has been very common. Again, that's one of good things for your future career. You guys in manufacturing, maybe powder metallurgy, finding more and more market because you're wasting less material. So the way it works, you make the metal, you transfer a metal to a powder, which can be done easily. And now you compact powder into the shape that you want, and then you put it in an oven, you cook it. And it's good when you are making self-lubricated gears. Again, self-lubricated gears, and they have like this, like the one that I show on the left here. I wish we were in an in-person setup, so I have a bunch of these gears. So I could give it to you and you could touch it. So it has an oily surface because it has all this porosity inside and it absorbs oil. So when it works, it has that smooth surface, and it's made by powder metallurgy. Anyway, you're going to learn about it later, either if you are mech or manu students. And then CNC, of course, especially for helical gear, CNC, it's been used a lot. You can read about it later more. It's not the focus of this lecture and this course. It's just a quick intro. And gears, of course, we need to do surface treatment. Like the surface, the outer surface has to be hardened enough. Otherwise, it gets break and it gets damaged and it's not going to work properly. Or people put coating on it to make the surface harder. And as I said, if they are plastic or polymer, then they can be made by injection molding, which for most of the toys, and they are super, super cheap. Let's get to some serious stuff. Kinematics of spur gears, okay? So for simplicity, I just showed here for two gears being involved with each other, just one teeth from each gear, okay? Gear 2 and gear 3. So you can visualize the rest. This is just two teeth being involved. So we want to treat it with the knowledge that we have so far. We can assume 2 is being joined here at point A, and member 3 is being joined at point B, and they are in contact at point Q, right? So first of all, if this mechanism, if I want to find out its degree of freedom, everybody, I want you to find the degree of freedom for me. So this mechanism has 3 members, right? So one always is ground. That's member 1. And then we have member 2 and member 3. And then you can type it in the chat. So degree of freedom, if you forget, that was the formula, 3n minus n, sum of the constraints. What is the answer here? The degree of freedom. You can type it in the chat. So I can see 1. What about the rest of you guys? What numbers you will get? So obviously n here is 3 members, right? The rest of you guys, did you find 1? So, and okay, maybe you can check with my solution later. Whenever we have a pin, we said the constraint is 2, right? So here is 2, u is 2, and here u is 2. The point of contact here, q, it has both rotation, because look at member 2 and 3, they are rotating against each other, and also they are sliding on top of each other. So the point of contact is roll and a slip. And if you remember, we said u is 1 for this guy. So anyway, you will get a degree of freedom of 1, which makes sense. This mechanism has 1 degree of freedom. It means if you give motion to 1, you can find the other one. So then there must be a relation between omega 2 and omega 3. We want to find it. The next step, let's find the instantaneous center of velocity. And we know how to do that, right? And this picture showed it for us. So we have 3 members, right? And we should have 3 instant center. So you can see I12 is that pin, I13, the next pin, right? So I12 and I13, they are clear. And please pay attention to this part. So you need to have a good understanding what's happening here. So we know I12 and we know I13. Another things that we know is the point of contact. If you recall, we solved one example. It was, I guess, a cam or something, that if 2 members, they are in contact with each other and there is a rolling and a slipping between them, then their center must be on a line, on a normal line, not in infinity, somewhere on a normal line, but we don't know where. Then we have another relation, which, if you recall, there was the name of 2 US presidents. No, one of them president, another one a governor, Arnold and Kennedy rule, which says that 3 center of velocity must be on the same line. So this mechanism has 3, 1, I12, I13, and I23. These 3 must be on the same line. That's the Arnold-Kennedy rule. So based on that, obviously we can find the I23, which is here, like intersection of the horizontal line and this normal line. Okay, so this is the normal line. So far good? If we are good, now I want you to write for me the relation between omega 2 and omega 3. Remember, we had something which we could write omega 2, omega 3. And you can write it in a chat for me. So over here, we like to have omega 3. So what should be here? And over here, we have omega 2. What should be there? Like the instantaneous center, you know them. What should go there? And you can type it in the chat. Okay, good. 2 answer popped up. Exactly. Oh, that's good. All right. So probably the rest of you could guess, right? Here we have to have 1, 2, and 2, 3, the distance between them, right? And here we have 1, 3, 2, 3. Remember this formula? So they are coming back to us, right? So you need to learn all the topics in the past so you know what's going on here. So I have this relation here, and if I look at this relation, then let's, for simplicity, so this I1 to I2, 3, 1, 2, 2, 3, it is like this distance A to P. And this guy is B to P, right? Omega 3. Let's, for simplicity, call this one R2 and this one R3. So I can then conclude that omega 2 over omega 3 is R3 divided by R2. And this is what we call it the velocity ratio. And you see the velocity ratio depends on the radius. And it's opposite to radius, right? Omega 2 over omega 3 is R3 divided by R2. And it's not a magic formula. It comes from the instantaneous center, which we learned before. Okay, so let's focus on this point P here for a little bit. This point P is what we call it a pitch point. Okay, another terminology alert. So this point P, we will call it a pitch point. And you realize this point is the instantaneous center between the 2 gears, as we prove it here. And this pitch point P, if you remember, was that point that we said 2 circles are rolling against each other, right? So these 2 gears, then if I want to show them, let's say there are 2 circles, one like this circle 3, and another one like this circle. Okay, these 2 circles, like these 2 gears, but 2 imaginary circles, they are rolling at point P. And as you can see, these 2 circles, they are not the outside circle or inside circle. Let's summarize this, the formula that we have. So based on what we learned before, this is a relation that we can write between the 2 velocities, right? And it gives us the velocity of point I23. And the velocity of point I23, like this point P, for these 2 gears, no, not that one, is the same for both of gears. So this is VI23. VI23. Okay. So that's the assumption. Unless the 2 gears, they are loose and they are not meshing with each other properly. If they are meshing properly with each other, that point is rolling. Keep in mind that point is rolling. Point P is rolling. And that point P, do not make a mistake, is not the point that they are in contact with each other. The point they are in contact with each other is point Q. That's a different point. Where that point comes from instantaneous center. And how we should visualize it: draw a normal line where two gears are in contact, where two teeth are in contact, and then the center line, the intersection of these two. And as I wrote in the previous slide, we call them R2 and R3, and we will find this value. And since the radius are constant, this constant is called velocity ratio. Okay, so if you go with a very small radius to a very large radius, then you're going to get a small velocity ratio, or vice versa. So we'll talk about pitch circle, right? And pitch circle, we said, is the circle that is point P. Again, I'm repeating it several times to make sure that you guys understand. Pitch circle for each gear, like the circle, again, if I can draw the circle here, that circle there, and that circle there, maybe not perfect. Move it a little bit there, bigger circle. And these two circles, as you can see, they are rolling at point P, which is that instantaneous center. We call that point pitch point, and these two circles, we will call them pitch circles. And that's the most important circle for a gear. When we talk about diameter of a circle, we're talking about this pitch circle. All right. So the diameter of a circle is not then again what we measure outside of a gear or inside gear. Is this diameter. And yeah. So I wrote it here, and I emphasize again here, diameter of a gear is this pitch circle diameter, is the diameter of this pitch circle. Okay. And then we have another circle, which we call it a base circle. What is a base circle? Well, if we draw two circles that they are, this is the last topic for today, and in 1 minute we will be done. This is the normal line, right? This is the normal line. If I draw two circles, which is tangent to this normal line. Okay, let's try to do that. So one circle, maybe that one. Okay, almost. So the circle center is at point B, and it is tangent to this normal line. And another circle for the other one, again tangent to this line. These are basic concepts, but believe me, many unfortunately students, like mech students, if you ask them, they don't know. But these are all important things that you guys should know. Because later you're going to design gears in your other courses or in future career. So these two circles, then we will call them base circles. Where they come from, center at A and B, and they are tangent to this normal. And these two circles are also important circle, which we can base many of our calculations there. And you will see them on this picture on the left. Now you see the difference between pitch circle and base circle. And again, I emphasize they are not the outside or inside edge of a gear that you can see. So let's stop here. And the next day, we'll talk about involute profile, which is an important, again, concept before we move forward with the future topics. Okay, please review what this lecture before attending the Monday lecture. And good day. I'm gonna stop recording here. And if you guys have any question, please feel free to ask. So where should be, okay, so that's there, stop there. Okay, it's a sunny day. Hopefully you guys, I know you guys are busy, but hopefully you can find some times to go out for a walk. Recording.